Hello. In previous lectures, we discussed Cauchy Riemann conditions and we explored the different forms of Cauchy Riemann conditions. Today, let us do a few more things regarding Cauchy Riemann conditions and the analyticity of the function. So, before that, let me just write one sort of notation here. So, if omega is a subset of R square and U be defined from omega to R, be a continuous function, be a continuous function, then U is called C1. This is the notation. It's called C1. It is also in terminology we say it as continuously differential function. Continuously differentiable function if both ux and uy exist and are continuous on this omega. So if this is the case, if the function is continuous and both the partial derivative exist and they're continuous, then we'll say that this u is in the class 1 function, where you can say these are continuously differential functions. Okay, in fact, we can generalize it. Generally, we can say that if A belongs to natural, U is said to be in class CK functions over the domain of definition omega. I would say in English, I would write it here that K times continuously differentiable functions. If all the partial derivatives of u up to kth order exist and are continuous as well. So these two notations you have to keep in mind because probably we may use it somewhere here and there. So I forgot to tell you this. Now, in previous lecture, we've already seen some important things in regards Cauchy Riemann conditions, and we spent 2 lectures on it. So now, today is the right time to explore a few more things regards Cauchy Riemann conditions and analyticity of the function. So now we've already seen a few important concepts. Now, let us take an example and try to take things from there on. Okay. So consider a function, let's say fz, which is nothing but imaginary part of z into the real part of z, this all modulus, and raised to power 1 over 2. Okay. If I take this function, what is good about this function? Again, this serves as an example. This is an example where the function fz satisfies Cauchy Riemann conditions at origin, Cauchy Riemann conditions at origin, but it is not differentiable at origin. But it is not differentiable at origin. So you have to keep in mind that I have told you many times that if function is differentiable, then Cauchy Riemann conditions hold. If Cauchy Riemann conditions do not hold good, then function is not differentiable. But if Cauchy Riemann conditions hold true, then it doesn't imply that fz is differentiable at that point where your Cauchy Riemann conditions are holding true. So this is something very important, okay? Okay, so to this end, we will try to find the validity of Cauchy Riemann conditions at first, so that you'll be able to get what I am trying to make, write the point. So just give me a minute. Okay, so let us first try to find what would be ux. Okay, so first let us find ux at 0, 0. It would be equals to what? It would be equals to limit h tends to 0, comma 0 minus u0, 0 divided by h. And certainly, uh, you know that this is fz is what? Fz is simply root over x into y. So clearly this is your u only. So it will be like 0 minus 0 divided by h, and it would be 0 because you know if y is 0, then this part would be 0. Okay. What would be uy at 0, 0? Clearly uy at 0, 0 would be equals to what? Limit k tends to 0, u 0, k minus u 0, 0 divided by h. Again, it is equals to 0 minus 0 divided by x, sorry, k, and certainly it is also equal to 0. Vx is already 0 because v here is nothing, because you know there's no such iota component here. So function fz is equal to u plus iota v, and I know that v is what? V is clearly 0 here. So vx at 0, 0 anyway it would be 0, and vy at 0, 0 would be clearly 0. So clearly ux at 0, 0 is equals to vy at 0, 0 and uy at 0, 0 is equals to minus of vx at 0, 0. So therefore we can clearly see that uh, Cauchy Riemann conditions are in fact holding good at origin. Now let us address the main question. Is the function differentiable at origin? Okay, so that is why I took this example to make you understand. I've taken many examples now, I think, just to reinstate this concept time and again, because it is a really important concept. So the next thing is, uh, whether function fz is equals to root over x into y is differentiable or not at origin. This you have to see. So clearly, in order to see that, I'll let me just do a little bit of mathematics. And what I'm going to do, I'm going to write this real part of z into imaginary part of z root over in some different way, and that would be like this. So I would write simply z square. So z square gives me what? Obviously, z square gives me z square gives me what? Z square gives me x square minus y square. So I'm writing it here somewhere so that you'll be able to get what I want to say. Uh, just give me a minute, sorry. Sorry. So let me just rewrite the function. So I'm rewriting the function. I'm writing it, rewriting fz. So fz is what? It is root over x into y. So I'm writing it as z square minus z bar whole square raised to power 1 over 2 divided by 2. Okay, so you can write this way also, or okay, if even if you don't want to write, let me write it this way only so that you don't get confused. So I'll do better thing. I'll try to write. I'll try to write. Um, I'll try to use rather. I'll try to use polar coordinates. That would help me, right? Okay, it's better to use polar coordinates. So we are talking of origin. Now let me, in polar coordinates, you know that x can be written as r cos theta and y can be written as r sin theta. Or simply, if you want to write any complex number, it can be written as r e to the power iota theta. So now let us come to the point. I was thinking that I could do something with this. It's better that I'll use polar coordinates then. Okay. So now, in order to prove that function is differentiable or not, what I'll do, limit s tends to 0, f of h minus f of 0 divided by h. This limit should exist and it should be what? It should be path independent. That is, in no way, two different parts should lead to two different limits, or that so on and so forth. Okay. So if I'm taking different paths, if I'm getting different limits, then obviously the limit is not unique. And therefore, I would say that limit doesn't exist. And therefore, if this limit doesn't exist, then function is non-differentiable. Okay. So we have known that if function is differentiable, then this limit exists uniquely. So what I'll do, I'll simply write h is equal to some del e to the power iota theta, where del tends to 0. So limit del tends to 0, f of del e to the power iota theta minus f of 0 divided by del e raised to power iota theta, right? This is how it would be. And f del e raised to power iota theta is what? It is simply, so I know that what would be, it's like root over real part of h into imaginary part of h. And I know that real part of h is what? Real part of h would be simply del cos theta. And what would be imaginary part of h? Imaginary part of h would be simply del sin theta. So it is root over del square sin theta cosine theta minus 0 divided by simply del cos theta plus iota sin theta. So any day, I mean, this is going to be what? This is going to be del root over sin theta cosine theta. So I can multiply with 2 and divide by 2. So I think del root 2. And here what I'm getting here, I'm getting cos theta plus iota sin theta, and then del is here. Okay. So this will become 1 upon root 2. So after all, I'm getting e raised to power minus iota theta divided by root over 2 into sine 2 theta raised to power 1 over 2. So clearly, this depends upon theta. And since it depends upon theta, it depends on the orientation of the complex number. And so therefore, I would say it depends on the path as well. And it is a path independent limit. So the path dependent limit. So therefore, function is not differentiable at 0. So I think these important concepts we've already discussed. But I just wanted to okay. The last concept that we were discussing was that, I think if I know, okay. So last concept that we were discussing was this, that if f of z is constant in some domain D, that is a connected domain, I'm talking of domain D, then f dash z is equal to 0 for all z belongs to D. And converse is also true. And conversely, if f is analytic in some domain, so being analytic means what? It is differentiable in any open neighborhood containing this point D. So for every point in D, it is going to be differentiable. So f is analytic in some domain D. And if f dash z is equal to 0, then f is a constant. So both of them hold true. And remember, the connectedness is an important criteria. Otherwise, you won't be able to get it. So just in order to give you a little bit of idea as to how I have created it, I know already in one variable calculus, if function is differentiable and it is equal to 0 for some interval, so let's say a comma b, then I can say that fx is a constant on some interval. Okay. So mind you, interval is necessary. Okay. The connectedness is compulsory. Okay. So on this line, I'll try to write a few things here. So let us suppose that z is element of D, and let's say z is equal to what? Let's say z is equal to x plus iota y, and let f is equal to u plus iota v. Okay. I already know that what is f dash. F dash can be written as ux plus iota vx, or if I want to write f dash in terms of uh, partial derivatives of u and v with respect to y, then this is it. I hope these two things you already know. Now let us suppose that f dash z is equal to 0. Suppose f dash z is equal to 0 in some domain D. Okay. F dash z equal to 0 means what? All these things are 0. It implies all the partial derivatives. All the partial derivatives, that is ux, vx, uy, and vy are all 0, isn't it? If f dash z is equal to 0 in some domain, then all the partial order derivatives are also 0. This is what I want to say. That is, if I want to write ux at some point x comma y, it would be uy at some point. This would be vx at some point, and sorry, vy at some point. All these fellows would be 0. You can write 0 here, and then you can do a comparison, and you can know that ux, uy, vx, vy are all 0 here. Okay. In one variable calculus, we already know. I'll write it here so that in one variable calculus, we know that from one variable calculus, rather, I would write from one variable calculus, we already know that if phi is some real valued function, phi belongs to R, that is a real valued function. If phi is a real valued function of a real variable and phi dash x equal to 0 on some interval, let's say a comma b, interval is necessary, please remember, okay? Then phi must be a constant. This is something we already know from our one variable calculus. Okay, so now let us let us try to make this assumption, let us try to make things easy now. Okay, now we already know that we already know that what? We already know that ux, vx, vy, uy are all 0. Now let us take a point. Let us consider an arbitrary point. Let us consider an arbitrary point. And what is that point? Let's say point z naught, and this, let's say x naught comma y. Okay. And now let us consider a horizontal line. So horizontal line means what? A horizontal line is always parallel to x-axis. Here y is a constant. So horizontal line means y should be constant. So I'll consider a line L constructed in a manner that I will put y is equal to y naught. So it is like equal to x plus iota y naught. And here, what condition I'm giving? I'm giving condition that x must lie between a comma b. So it would be a line segment whose length, who would vary from a to b. So let's say here is a, here is b. So I'm talking of a line segment here. Okay, and y is a constant here, and here I will write y is equal to y naught. So this particular segment of line I have represented in this fashion. Okay. Okay. And this particular thing. Now, if this horizontal line lies inside D, lies inside D. D was what? Domain D. Okay. Where your U, V, X, U, V, like FZ is defined on D only, na? So U plus iota V. So where your U and V are defined. So if this lies inside D, then what happens? Then I can define my phi X simply as what? Simply as U X comma Y naught. Let me define phi as U X comma Y naught. And I know that if I'm going to differentiate with respect to X, Ux, I'm going to get 0. So if I differentiate on both sides, I'll get phi dash X equal to 0 on what? On this line segment L. So what I've done, I have defined my function phi X, where X should lie from D. And what I've done, I've written my function U in a way that I've constrained my Y. So basically now this becomes a function of X. So phi X is, I'm defining it as U X comma Y naught. Since I'm taking X and Y both from D, so this is well defined. If I differentiate both sides with respect to X, I get phi dash X equal to 0 because I already know that Ux is 0. So therefore, phi dash X is 0 on the line segment L. Line segment end. So therefore, it is U is a constant on L. Okay. So therefore, it is constant on any horizontal line. So I can do this for any arbitrary Y naught. Obviously, that Y naught must be constrained in the domain D. So for every line Y naught, I can do the same thing, and I can always write that U is a constant along any horizontal line. Likewise, what I can do, I can simply write my phi Y is equal to U of X naught comma Y, and I can write Y belongs to C comma D. And again, if I differentiate both sides with respect to Y, what I'll get? I'll simply get Uy at X naught comma Y. And I know that this is particularly 0. It implies that phi Y is 0. What does it imply? It implies that, sorry, phi Y is a phi dash is equal to 0. It implies phi Y is a constant, and it implies that U X naught comma Y is a constant on line segment L. It implies what? It implies that U is also constant on any vertical line segment. Now remember that D is an open and connected set, right? And each point on D can be connected by what? Polygonal lines. Any polygonal lines. So if I take polygonal line, I can take these vertical and horizontal segments also. Each point can be connected by these vertical and horizontal segment. And I know that on each of these points, my U is a constant. On each of these points, I know that my U is a constant. So therefore, I would say that my U is a constant on complete domain D. Similarly, I can construct the same thing for V. And if U and V are both constants in D, it implies what? It implies that Fz is constant throughout D. So this is how we do the proof. Just wanted to make you, I mean, I'm not doing some very difficult proofs. A few of proofs I would rather tell you to find in book only, because these lectures are mainly to cater your competitive exams. But still, uh, whatever I can do in little bit of time, I would give you hints and so on and so forth. So I hope this is quite clear. Okay. Many proofs you would find in complex analysis that they're connected to uh, proofs in like proofs in calculus, multivariable calculus. So if you are well aware with multivariable calculus and proofs there, so you will be very and you'll be at ease while doing all these things. So today we are going to do a few more things, and let us see a few more definitions. Okay. So now let us do one important stuff, and that is this. See, if this is important, please remember, if one of me, if fz, if नहीं ऐसे करते हैं, if fz is analytic in domain D, fz is analytic in domain D, okay? Now, if first I'm writing f mod is constant on D, then f must be a constant. So this is the important thing, okay? See, if f is analytic in domain D and mod f is constant on D, then f must be a constant function on D. Okay, let us see how. Let us see how. So, see, what is f mod? So first, let me write fz. Fz is what? Fz, I know already it is equals to what? So I'm going to write it here. Yes, okay. So I already know that my fz is equals to what? It is equals to u plus iota v on domain, let's say D. Okay. And what would be fz mod? Fz mod would be simply, um, it is given it is equals to k. So I would prefer to write it in square, like u square plus v square is equal to k square. Okay. Since fz mod is given to be equals to some constant on D, so I'm writing fz mod is equal to k. So u square plus v square is equal to k square. Is that fine? Now, if I differentiate it with respect to x at first, so partially differentiating, with respect to x and y, what we'll get? We'll get u into ux plus v into vx is equal to 0, and u into uy plus v into vy is equal to 0. Okay. And already we know from, because function is analytic on domain D, so ux must be equal to what? Vy. Since I'm writing f is analytic on domain D, then ux must be equal to vy and uy must be equal to vx. This we already know. Okay, so if I write this way, so I'll get u into ux minus v into uy. This will be my equation number 3. And then another equation would be u into uy plus v into ux would be equal to 0. Equation number 4. Okay. So what I can do, I can do a little bit of mathematics. What I'll do, I'll square this up and I'll add. So if I square 3 and 4 and add them, what will I get? I'll simply get u square ux square plus v square uy square plus u square uy square plus v square ux square equal to 0. And if I take ux square common and uy square common, so what I'll get? U square plus v square into ux square plus uy square. is equal to 0. And I already know that this particular fellow is what? It implies what? Implies that k square into ux square plus us square must be equal to what? 0. Anything, any square quantity is always greater than equal to 0. So the solution from here would be ux equal to 0 and uy equal to 0. Okay. And if ux and uy are constant, it implies that u is a constant. If u is constant, then v must be a constant function, because if ux is 0, then vy is 0, and if uy is 0, then vx is 0. So therefore, u and v are both constant. It implies that fz must be a constant function. Now let us move to another